Thank you for joining another exciting vibration research webinar. Last month's webinar with Mark Brown was about accelerated vibration testing for batteries. Today, we are going to continue that discussion and talk about the correlated relationship between the real-world vibration environment and accelerated vibration testing for batteries. Our aim in this presentation is to answer the question, how can I correlate my accelerated vibration test to the end-use environment of my intended market, even if I have little or no measured data on my product? This situation can happen for a lot of reasons, ranging from being so early in product development that prototypes are not available to gather data on, to not having the right data acquisition equipment or knowledge of how to get the data and to process it. Knowing the answer to this question, however, is critical for developing accelerated vibration tests that confidently demonstrate reliability targets, minimize warranty claims, and make the most efficient use of laboratory equipment to meet ever-stringent product quality attributes on shrinking product development timelines. In today's webinar, I'm going to talk about how Vibration Research's Observer 1000 along with ObserView software can be used to develop accelerated vibration profiles that are properly scaled for frequency content, amplitude distribution, and test duration. In other words, correlating your vibration test to the real world. These techniques are essential for avoiding the pitfalls of either over-testing or under-testing, and for providing confidence that your test results are meaningful. We will talk about Vibration Research's tools, battery vibration failure modes, and use a case study to demonstrate a method for arriving at parameters for an accelerated vibration test that, if executed properly, you can be confident about. Vibration Research delivers unique value to its customers in terms of field data acquisition, data analysis and processing, and test development. In many cases, customers do not realize the power of the tools and how easily they can be applied to improve product development results and timing. Please use the chat feature to let me know if you have any questions or comments during the presentation. We will be sure to get back to you after the webinar. Vibration Research was established in 1995 by John Van Baren and his wife Valerie. John was a mechanical engineer with considerable experience in shaker technology and vibration testing. He envisioned more realistic methods for vibration control and set out to make them a reality. About a year later, John's brother Phil Van Baren joined Vibration Research. Phil is an electrical engineer with a gift for transforming complex theoretical concepts into advanced vibration testing software. Since 1995, Vibration Research has become the leader in sound and vibration technology. My name is Tom Achatz. Prior to working with Vibration Research, I spent many years, decades actually, working in validation testing of automotive components. When it came to solving complex vibration problems, I always found that Vibration Research was ahead of the pack in innovation, collaboration, and support. The people at Vibration Research have built a great company ready to help you make your product better with shock and vibration testing done right. Vibration Research is still family-owned, but it is now the global leader in vibration control. Currently, Vibration Research controllers are operating in over 60 countries. To maintain our global footprint, we have additional sales and support offices in China, the Czech Republic, Germany, India, and the United Kingdom, and industrial representatives in many other countries. Naturally, vibration testing is used globally in many industries, from automotive to aerospace, electronics to package testing, and defense systems to seismic design. Virtually anything that moves, shakes, or is subject to an impact may require vibration testing, and that is Vibration Research's focus. This variety makes my job fun because I interact with new products, technologies, and testing requirements every day. Plus, I meet with all kinds of customers. Here's a brief timeline of Vibration Research's most significant innovations. Each feature has revolutionized the vibration testing industry and allowed for more realistic testing and reliable results. Our competitors are still scrambling to keep pace with us. Staying at the leading edge of control testing technology makes our customers successful and fuels our own success. Our first innovative feature, field data replication, differentiated Vibration View from the other controllers on the market back in 1995. This software module allows for the one-to-one replication of field environments in a non-iterative process. The underlying algorithms allow our field data replication tests to reach full level quickly, saving our customers time and money. The next innovation was Kurtosion in 2005. This patented technology adds kurtosis to a random waveform, allowing the peak accelerations reflected in the real world, even around resonances. Other forms of kurtosis injection dampen the peaks out. In 2010, we brought fatigue damage spectrum to the market. FDS creates random vibration tests based on field data, approaching a real-world environment as closely as possible in an accelerated testing timeframe. We will be talking a little bit about that in today's webinar. IDOF, or Instant Degrees of Freedom, improves the accuracy and reliability of the short-duration random tests commonly used for expensive launch systems and complex payloads. It uses an advanced and patented algorithm to deliver accurate and low variance PSD estimates, calculated much quicker than traditional averaging. IDOF removes the estimation error while displaying the control error, providing the true difference between the PSD of the signal and demand. In 2020, we released STAG for sign-on random test generation, specifically for vibration environments with dominant sinusoidal content, such as found with engines. Most recently, TrueClip was introduced to reduce high sigma peaks on the shaker table. This clipping method applies to the control measurement and minimizes the chance of exceeding maximum acceleration, velocity, or displacement limits of your shaker. These are our most noteworthy innovations, but our products exhibit hundreds of other innovations covering math algorithms, usability, and user interface features. Vibration Research designs and manufactures vibration control and data acquisition systems for vibration testing on electrodynamic and servo hydraulic shakers. Most of the work presented in this webinar was done using the Observer 1000 data acquisition system with its companion ObserveView software for analysis. The Observer 1000 represents a new generation of technology for field data collection and analysis. Designed for mobile use, it is compact and weighs just 1.5 kilograms. It is also battery powered and has an integrated SD card for data storage. The device supports test configurations with up to 16 channels using a smartphone or tablet via a wireless connection. After setup, users can monitor and control tests wirelessly or let them run autonomously. While the VR9500 controller and Vibration View software are designed to create, control, monitor, and report on lab tests, the Observer 1000 and ObserveView products are designed to collect, analyze, and report field test data. The Observer 1000 is a mobile, battery-powered standalone device. It has inputs for microphone, GPS, tach signals, and easily measures acceleration, pressure, strain, load, etc. Several of its significant features are listed on the slide. Probably most significant is that the hardware is controlled by the VR mobile app, which runs on a smartphone or tablet using a Wi-Fi connection. Tests can be set up, monitored, and modified in the field without a wired configuration, delivering both flexibility and simplicity to field tests. Collected field data is stored on an integrated SD card. When the field test is completed, the data can be transferred to a PC for analysis by moving the SD card or by using an Ethernet connection. Data analysis on a PC is implemented using the tightly integrated ObserveView software, or for some types of analysis, using Vibration View and an Ethernet connection. With ObserveView software, users can view, edit, and analyze waveforms from recorded or live data. This powerful and efficient vibration analysis software includes specialized modules for waveform recording and test generation. The Live Analyzer view displays a live stream of data from any VR hardware. The user can pause live data playback to analyze an event, and the data will continue to stream in the background without loss. ObserView's primary function is as a time waveform editor. It can perform operations such as cut, copy, or paste, and allows adjustments of transition fade options. However, ObserView also offers many opportunities for analysis. Additional software options include modal testing, octave analysis, PSD, FFT and spectrogram analysis, order analysis, sign-on random test generation, fatigue damage spectrum, test spectrum generation, live FDS, and shock response spectrum. We'll be using ObserView software in our case study today. With battery electric vehicles expected to account for nearly 30% of vehicle sales in 2030 versus about 4% now, the need for battery testing has never been more critical for public safety, vehicle reliability, and product performance. There are many examples of costly product recalls, plant shutdowns, and liability claims arising from electric vehicle battery failures that were not identified but could have been during product development. For an electric vehicle battery to survive the severe end-use environment of drivers over sustained periods of usage, while satisfying the ever-changing arena of regulatory requirements, OEM criteria, and customer expectations, demands that attention be paid to the details of good analysis and testing, particularly with respect to vibration. While many companies have at one time or another relied upon vibration test standards passed down from internal combustion engine architectures, such practices are generally inappropriate for battery electric vehicles. In some cases, they have been used either out of convenience or for lack of understanding. Ultimately, this practice leads to false passes and warranty claims or to false failures, causing unnecessary and costly product development, iterations, and delays. So why do we test? Are we testing simply to meet OEM or regulatory requirements? Or are we testing because we want to deliver a superior product that will withstand the rigors of severe customer usage over a long period of time and do so safely, reliably, and without performance degradation? Hopefully for the latter reason, which makes not only for a better product, but also for a more enjoyable and challenging experience as a test engineer. The ability to confidently guard against performance degradation, safety hazards, regulatory violations, and reliability weaknesses is paramount to the success of any battery manufacturer or OEM. When we think about battery vibration testing, there are several common failure modes found in battery packs. One of them, loose connections. So vibrations can cause the electrical connections between batteries to become loose, reducing the conductivity of the pack. You have mechanical damage, in which vibrations can lead to the mechanical failure of the battery pack, causing the outer casing to crack or deform, which could potentially result in internal damage, including seal breaches and leaks of coolant lines and so forth. You have broken welds. So battery packs consist of numerous welded components such as cells, connectors, and leads. Vibrations can cause these welds to fatigue, leading to broken weld joints. Shorts. Vibrations may cause battery cells to shift, resulting in short circuits between positive and negative terminals. Degradation of material. When batteries are subjected to high-frequency vibrations over long periods, mechanical fatigue and degradation of materials, particularly at the joints and bonding points, is likely to occur. So these are just a few of the many possible failure modes that can be found on a battery pack or on battery components due to vibration. A good vibration test correlated to the end-use environment over the design life of the product goes a long way to mitigating the likelihood of these and a multitude of other potential failure modes. Tests must have proper scale. So whether we're testing a component, subsystem, or a system, defines to some extent what the appropriate equipment and what the appropriate process to derive a profile should be. Tests must replicate real failure mechanisms and failure modes. So to do that, we should start with a solid DFMEA and know what you are looking for in your vibration test before you begin. The test must be correlated to the end-use environment. This is essential to understand correct levels and duration of testing. Tests should be accelerated. Testing needs to be as short as possible, include the corner points of environmental loads, but not produce foolish failures. Tests must support knowledge base for math models. Assumptions and boundary conditions for digital twins need to be confirmed for modal analysis, resonance avoidance, fatigue resistance, and design robustness. There are many vibration test methods to choose from that may or may not be appropriate for your product and where you are in the development phases. One of them would be HALT or RFMPT. So it's a highly accelerated life test or a rapid failure mode precipitation test, in which we identify latent failures and fix design early. It's quick and dirty, it's generally not correlated, and failures may be foolish or real. But it's an opportunity to find things that could break that we could fix before we get into the longer, more detailed correlated tests that prove out our design. Sinusoidal vibration testing applies vibrations with a constant frequency and amplitude, whereas random vibration testing can simulate real-world vibration conditions by applying a range of frequencies simultaneously. So these are appropriate for our design validation and our process validation. STAG, which we talked about earlier, the sign tracking, analysis, and generation, is appropriate for products that have rotating components. Highly accelerated stress screening is used once the product is in production to assure ongoing quality. And we can't forget that in addition to just vibration testing, we have to consider mechanical shock testing to assess the battery's response to sudden, high-intensity, transient shocks. All these methods and several others could be discussed in detail, require an understanding of customer and end-use environment. So there are 4 possible outcomes for an accelerated vibration test. You can have a true pass, true fail, a false pass, or a false fail. A true pass is meaningless if the underlying test is incapable of producing true failure modes. As a result, high-fidelity application data with correlation to end-use environment is essential. Vibration test specifications are often written as success run, so that suppliers and OEMs can accurately predict test cost and timing. In a success run test, we know the length of the test, and unless there's a failure, we consider that it has met all the requirements. Although test to failure methodologies are more useful in many respects, even they must have correlation to end-use environment to yield meaningful results, and their durations are unknown, causing many scheduling problems in the product development big picture. When a true fail occurs, and you know it is a true failure because you have confidence in your test to field correlation, the test engineer becomes an organizational hero, even if the designers do not want to hear the news. There is often significant organizational pushback when failures are identified on test. However, the test engineer, armed with irrefutable measured data to correlate to end-use environment and established test acceleration methodologies, such as offered through ObserView software, has no problem convincing the organization that a design change is required to avert problems down the road. This is where the Observer 1000 and ObserView software come to the test engineer's rescue. False passes are never good, but are a frequent occurrence when companies look back at their validation testing and compare to warranty claim data. False passes lead to product recalls, warranty costs, liability, and harm to reputation. Fortunately, when tests are specified well from the get-go with good field data combined with sound methods for test development, false passes are less common. Finally, false fails are almost as disastrous as they lead to having to scrap or rework costly prototypes, resulting in loss of time, unnecessary investigations, and design changes, not to mention the additional costs and time delays associated with the need for further product testing. When good data is gathered at the outset of product development and processed into good field-correlated accelerated tests, false fails are a thing of the past. While industry standard tests for vibration have their place, there are so many available and constantly changing that it is difficult to know which one is right for any given battery pack architecture and configuration. The common standards today vary significantly in terms of frequency, anywhere from 7 to 200 hertz or 8 to 1,000 hertz, etc. Amplitudes that vary by axis, durations from 3 hours per axis to 38 hours per axis, industry standards that include sine sweeps or are just random or both, mechanical shocks that have 150 Gs, 6 milliseconds, or 10 Gs for 16 milliseconds, and the number of shocks, 3, 10, who knows? So which of these is right for you? We don't know. But if we measure and understand our end use environment to develop a correlated test, we will know. And for this, the fatigue damage spectrum is a very robust tool. In the end, it is faster and costs less. The Observer 1000 and ObserView software makes this relatively easy. So we need reliability at the right cost. Delivering the right performance and reliability at the right cost is critical to success in the highly competitive and safety-intense arena of batteries. Different vehicles place very different loads on their components, and as a consequence, generic test specifications for batteries cannot adequately address the range of applications coming on the market. In many cases, failures and failure modes found after start of production were not caught in testing with generic specifications. The flip side also has been shown to happen. Failures in testing that were not seen in the field. Testing to generic specifications can lead to overdesigns, which add considerable cost. So bad testing is no testing. Gaining upfront knowledge of failure modes, mechanisms with objective pass-fail criteria is essential. When supported with good measured field data used to develop a customer correlated test, the risk is mitigated early and probability of issues down the road is minimized. Gathering accurate and relevant field vibration data has its challenges, but as we will show with our case study, these are not insurmountable. First, what sources of data are available? Ideally, you'll have the product, the necessary data acquisition hardware, and a suitable place to gather data in the form of an RLDA, which is a road load data acquisition. This is certainly not always the case, though. The next best alternative is to use surrogate data gathered from previous similar programs that serve as a good starting point until better data can be measured. Finally, with some searching, statistical data of customer usage can often be found and used as a foundation to begin your program. Secondly, having the right data acquisition equipment can be a challenge. Data acquisition systems such as the Observer 1000, along with transducers and wiring, are required. Optional equipment that aids in understanding and post-processing the measured data include a GPS, microphone, camera such as a GoPro, auxiliary channels such as strain, pressure, temperature, etc. are also great aids to have. When collecting field data, first, define the purpose of the test. Are we in the early development? Are we going to run a halt test, the RFMPT test, or are we looking to find out what breaks? Are we in design development, answering the question, is this design going to perform? Or are we in the process validation phase and trying to answer the question, is this product reliable in the hands of our customers over the intended design life? We need to know the events to record, how they relate to severity, X of a design life. So is this product going to be used in China and South America, North America, Canada? Is it a commercial vehicle? Is it a sports vehicle, delivery vehicle? What is the purpose of this vehicle? And that provides some insight as to what we really need to measure when we do our road load data acquisition. We need to identify appropriate measurement points. And these should be documented with drawings, photos, and a clear channel mapping with an understanding of why we're putting accelerometers where we're putting them. Are they to drive and control the test, or are they response? Are they to support a digital twin or some other purpose? We need to secure, attach, and route the cables for the transducers in such a way that we aren't introducing noise to our signal. We need to set correct recording parameters. So the calibration, the sampling rate, filtering, all of these things need to be thought of ahead of time and set up. Then we need to gather the data and perform integrity checks, because there's no point in processing bad data, right? If we have a problem with the data, we need to figure out what that problem is, fix it, and then go get the data again. And finally, process the data as required for the test. So whether it's a field data replication, or a shock test, or a field correlated fatigue damage spectrum test, we need to use the right tools, all of which are available in vibration research software. So interestingly, when we think about industry standards, the SAE J2380 standard for vibration testing of electric vehicle batteries has a wonderful statement in it, which I'll read here. It says, preferably a specific vibration durability profile should be developed based on actual vehicle measurements for the specific electric vehicle application. So what that's really telling us is that in this world of batteries, there are so many architectures and configurations, and they're coming out so fast that having one generic vibration standard for vibration is going to lead to false passes and false fails. So we should take the time to develop a specific profile as close as we can to our intended application and design life to correlate to the end use environment. The fatigue damage spectrum, which is a processing tool available in vibration research analysis software, is used to calculate a nominal damage target that represents a lifetime of use for the severity, customer, and environment that the product is intended for. The data from the RLDA or other sources then combined in such a way as to achieve the target damage in an accelerated vibration test. And we have a case study that we're going to look at how that plays out. So in our case study, we have also the shock response spectrum, another tool available in vibration research software, which establishes the upper limit for test acceleration to ensure that a vibration test is properly accelerated without over-testing, thereby causing false failures. The shock response spectrum for the field data is compared against the test, and the test duration time is iterated to achieve the optimal test duration. So we're going to show that in our case study. So our case study is involving a light delivery truck. And we should note that the design technical specifications for the product should include a design life requirement, indicating mileage, time in service, customer severity level, and a reliability target. This information is then used to weight the available data to scale the content and duration of the accelerated vibration test. In this case study, the usage for a light delivery truck could be easily approximated using information in the public domain. So we found a document from the Office of the Inspector General of the United States Postal Service, which summarized delivery routes into 3 categories that could be used to identify types of duty cycles to gather data, or to use surrogate data from previous programs or other sources, and then post-process using fatigue damage spectrum. The main idea, as Mark presented in last month's webinar, is to establish a field damage level to characterize the overall life exposure of the product. This, in turn, is used with weighted fatigue damage spectrum of the road load data acquisition, or the surrogate data, to generate the accelerated vibration test. The test is accelerated to stay within the bounds of the shock response spectrum of the field environment. As noted earlier, sources of data can be road load data acquisition, surrogate data, public domain, or even synthetic data derived from a virtual RLDA, which is becoming more and more common as our analysis tools become more capable and sophisticated. Let's look at how these ideas were applied to a battery pack for a light delivery truck. Based on the analysis of package delivery routes in the United States, the data that was needed for this particular program was highway, rural, in other words, gravel road, and city driving. As such, we invented about a 20-mile route that included all three of these road types. We then set up our Observer 1000 with a microphone, GPS, and accelerometers to measure the data over the invented route. We also included cameras. The data was then post-processed to extract snippets of the route that reflected the desired end-use environments. This screen is an actual screenshot from ObserView showing the identification and extraction of the portion of the route representing the rural aspect, the gravel road driving. It was as easy as dragging the cursors at the bottom of the screen where the entire route is shown and following along with the map and photos to isolate the gravel road section. The same process was used to isolate the highway and city portions of the data. Then, using the package delivery route analysis report to get the overall lifetime distance traveled over each road surface type, the distances represented by our snippets of data could be normalized with repetition values to achieve a representative aggregate usage profile for our design target. This was then processed using Vibration Research's fatigue damage spectrum to arrive at the target lifetime damage value for this particular application. The fatigue damage spectrum process was then applied to generate an accelerated PSD test profile scaled with the shock response spectrum iteration process to achieve an optimal test duration and amplitude for a test that we have confidence will yield only true failures. We then compared the results to the SAE J2380 standard as shown next. This slide shows the results of the case study versus the SAE standard J2380. The top left graph shows the fatigue damage spectrum field correlated fore, aft, and lateral accelerated test profiles compared with the SAE standard profiles, normalized to the durations provided by the SAE standard. The top right graph is for the vertical axis versus the SAE vertical profile. Interestingly, we can see that for the case study application, that the SAE profile is substantially over-testing the battery packs across the entire frequency band, except under-testing the 13 Hertz wheel hop content in the fore-aft axis, which is a significant miss. The three graphs on the bottom of the slide show how the case study shock response spectra for the field correlated accelerated test compare with the unaccelerated data normalized to one design life. The goal is to iterate the test duration to make the accelerated test shock response spectrum as close as possible across the frequency bandwidth to the unaccelerated field data. This ensures that the duration of the accelerated test is optimally set to reduce test time, but yet not produce foolish failures. While the SAE standard stops at 180 Hertz, generating your own profile allows going to higher frequencies to comprehend failure modes, especially on internal circuit cards that are sensitive to inputs of several hundred hertz. For this case study, and other similar work that could be done, we should always remain cognizant of underlying assumptions. For the comparisons we made for the case study, these assumptions could include that the lifetime usage of a light delivery vehicle can be derived from the U.S. Postal Service Inspector General's report. Also, that the SAE J2380 is based on similar measurement points. Unfortunately, the standard does not provide guidance as to what part of the battery pack these profiles reflect. Also, there's an implicit assumption that the SAE J2380 standard represents the intended target design life, but we don't know what they used for that design life. Without this understanding, it is difficult to correlate the test to field reliability connection between the accelerated test and the test standard. Caveat emptor, but at least make sure you understand the underlying assumptions and what that means for any test results. The SAE standard does not answer questions such as, on what vehicle over what roads was the SAE 2380 source data collected? Where were accelerometers located for the source data? What is considered the target design life? And how can SAE J2380 be used to make a reliability statement? In other words, how many battery packs do I need to put on the test and not have failures to state that I've met a certain reliability requirement? And lastly, how was raw SAE J2380 source data processed to arrive at a vibration profile? Do they use a fatigue damage spectrum, or did they use some other process? Going through the process described in this webinar allows you to understand how your test was determined and to have confidence that your testing results reflect what will happen in the field. Critical knowledge to minimize risk of warranty, liability, and other problems. This process also provides an apples-to-apples pathway to benchmark applications internally and with competitors. Using the Observer 1000 and Observer software, you can establish better evidence-based criteria to parse road load data acquisition data routes to target customers. You can benchmark multiple vehicles using consistent measuring points and RLDA parameters. The fatigue damage spectrum provides a clear path for doing this. You can measure vibration on internal battery components to improve robust design and/or find cost savings. And you can use that data to generate profiles to run specific component tests without having to have the entire battery pack to do it. You can use these results to improve your supply chain quality, reliability, and durability. You can also use the FDS methodologies to convince your customers or OEMs of the need for rigorous and customer correlated testing and how it saves them time and money. You can use it also to identify appropriate test equipment. So once you know what you're testing, how you're going to test it, and what the levels are, you can pick out what you need to actually run the test well. And you can use FDS methodologies to provide good virtual twin correlation. So to summarize, the key to success for automotive suppliers is to design components that meet reliability targets, keep warranty costs low, while at the same time achieve low production costs. Traditionally, automotive components are tested using generic specifications based on historic damage profiles with little connection to the vehicle that the component will be used on. The result is that the component may be over-designed for some types of vibrations while remaining vulnerable to others. How does VR make this whole process easy? First of all, the Observer 1000 is portable, and it works with a very portable. I mean, you can carry it in your hands. It's so easy. It's light. The VR mobile app has no external power source. It's easy to accomplish transducer excitation, calibration, etc., using your cell phone or tablet. You can readily get data from application or on test. The ObserView software is intuitive. Data is easy to check and understand with convenient copy-paste features and to analyze for all sorts of transmissibilities, coherence, PSDs, shock response spectrum, fatigue damage spectrum, etc. And the software has lots of tips and help embedded within it. There's an easy learning curve. There's lots of resources at Vibration Research, including their website and just phone call or email. Handles large data files seamlessly, and anyone can test with confidence, knowing how long and what levels to run the test. And that's absolutely the key thing here, and what this webinar is trying to emphasize is that you can do this and be confident that you have a good test. And you can use Cortosion, another VR innovation, to speed up the process. And of course, you have quick technical support. So the VR mobile that I discussed earlier is embedded in all Vibration Research hardware. The hardware communicates via Wi-Fi or Ethernet to the software running on a mobile device or a laptop. Users can configure inputs, set up data recording to the SD card, start and stop recordings, and view a live data feed. They can also view and configure input channels and efficiently navigate large recorded data files. Following this, they can download data recordings and analyze them with the many functions of the ObserView software. In conclusion, identifying real failure modes for the correct reasons is essential for effective use of product development resources. For vibration testing, this means having the right data, measured properly, and correctly analyzed to correlate an accelerated vibration test or virtual twin model to a known amount of severe customer usage. With the right tools and know-how, the process to acquire good data and use it to arrive at a vibration test profile with the appropriate frequency content, amplitude, and duration is readily achievable. In fact, for the case study, that work can be done easily in one day by just a couple people. Vibration research hardware and software gives test engineers confidence that their test profiles deliver field representative results. And finally, if you're going to run this test, make sure that you get a really good profile using these tools and what we learned in this webinar, but make sure that you're using the right test equipment, that you have a good fixture, that you have good control, and you understand what your failure criteria are before you begin testing, and you execute your test. Lastly, we need to make sure we consider not just the vibration aspect, but also mechanical shock data and testing. And vibration research has lots of tools for accomplishing those things as well. And to think about reliability in terms of liable analysis, sampling plans, and impact on test duration and test equipment. So to wrap this up, vibrations research's core focus is to make the world's most innovative sound and vibration technology tools, enabling our customers to make reliable decisions and trustworthy products. Our core values are collaboration, capable and competent, accountable and responsible, strong and driven work ethic, do the right thing, and innovation. These values govern our decision-making at a personal level and a company level. Most of our values are apparent to our customers when they receive assistance from vibration research support. However, the concept of innovation is most evident in all of our products. That completes our webinar about test-to-field correlation for accelerated vibration testing. As you can see, we are laser focused on vibration testing, and our products have an unmatched set of tailorable capabilities. Please use the chat feature or send an email to let me know if there's anything you'd like me to expand on, and I'd be happy to talk to you sometime after this webinar. Thank you again for listening, and have a great day.